Hey everyone, have you ever really stopped to think about what's going on inside your computer? I mean, deep down when you click on something or open an app. Well, today we're going to pull back the curtain on the CPU, the actual brain of your device.
Right? We see our computers performing what looks like magic every single day. They're rendering amazing graphics, crunching huge numbers, connecting us with people all over the world. But how do they think? How does a little piece of silicon actually make decisions?
Here's the wild part. All of that incredible complexity, everything your computer does, it all boils down to one single, really simple process. It's a core loop that just runs over and over again at a speed that's almost impossible to imagine. It's called the fetch, decode, execute cycle. So yeah, let's dive into this one idea. It's officially known as the CPU instruction cycle. You can think of it as the fundamental heartbeat of the computer. It's the single thought pattern that every single computing device relies on, from a massive supercomputer all the way down to the phone you've got in your pocket.
Okay, so to really get this cycle, we first have to meet the team inside the CPU. You see, it isn't just one monolithic thing. It's more like a highly specialized crew where every member has a really critical job to do. Let's get them introduced.
First up, we've got the control unit, or CU. This is the project manager for the whole operation. It doesn't do any of the heavy lifting or the math itself, but it reads the instructions and tells everyone else what to do, where to get their data from, and where to put the results. It's literally directing the entire show.
And next to the manager, you've got the real workhorse, the arithmetic logic unit, the ALU. This is the powerhouse, the calculator of the CPU. Anytime your computer needs to add two numbers, or check if one thing is bigger than another, or do any kind of math or logic, yep, the ALU is what's doing the work.
So, how does the CPU know what to do next? Well, that's the job of the program counter, or PC. It's kind of like a bookmark in a giant recipe book. It holds the exact memory address of the very next instruction the CPU needs to go and grab, which makes sure everything happens in exactly the right order.
And finally, we've got the registers. Think of these as tiny, super fast storage spots right there inside the CPU itself. They're like a little scratch pad on your desk. They all have very specific jobs, like holding the instruction you're currently working on or a little piece of data. We'll see some of these, like the MAR and MDR, in just a second. The big takeaway for now is that they give the CPU instant access to whatever it's working on right at that moment.
All right, so we've met the crew. Now let's follow one single instruction as it makes its way through the CPU. This is where we'll see how all these parts come together and work in this perfectly coordinated little dance.
Our little instruction is going to go through three main stages. First, the CPU has to fetch it from the computer's memory. Then, it has to decode it to figure out what it's supposed to do, and finally, it will execute that command. Fetch, decode, execute. Simple as that. Let's watch it happen.
To make this real, we're going to track a super common command, a load instruction. Its job is really simple. Go to a specific address in memory, grab whatever piece of data is stored there, and bring it back into the CPU. That's it.
Okay, here we go. The cycle begins. The program counter, our address book, says the next instruction is at memory address 0x1000. So the first thing the CPU does is copy that address over into the memory address register, the MAR. The MAR is now pointing exactly to where our instruction is living in memory.
With that address locked in, the computer's memory finds the instruction at that spot and sends it back to the CPU. And there it is, that value, 0x524C, arrives and gets placed in the memory data register, or MDR. And just like that, we've officially fetched our instruction.
Now this next part is just brilliant. The instruction moves from the MDR into the instruction register, the IR, where the control unit can take a look at it. But look, at the exact same time, the program counter has already ticked up to 0x1001. The CPU is already getting ready for the next instruction before it's even done with this one. Talk about efficiency.
So the control unit has now decoded that instruction. It sees it's a load command, and it knows the data it needs to grab is at address 0x24C. So it takes that address part of the instruction and puts it into the MAR. We are now pointing to the location of the data we need to load.
And just like before, memory responds. It looks at address 0x2A4C, finds the value stored there, in our case the number 150, and sends it right back to the CPU where it lands in the memory data register. The data has arrived.
And for the final step, the control unit moves that data from the MDR into another special register called the accumulator. This is a common spot to hold numbers for math and other operations. And that's it. The load instruction is complete. The CPU now has the number 150, and it's ready for whatever's next.
Now that whole journey, that might seem like a lot of steps, right? But your computer does this billions of times every second. How on earth is that even possible? Well, it all comes down to two key tricks that give the CPU its incredible speed.
First, it's all about the location of the workspace. Think of the CPU as a chef in a kitchen. The registers, they're like ingredients sitting right there on the countertop, ready to be grabbed instantly. Main memory, or RAM, that's like the pantry down the hall. Sure, it can hold way more stuff, but it takes time to walk over and get something. Using registers for all the immediate tasks is absolutely critical for speed.
And this number really drives that point home. Without those super fast registers right on the countertop, the CPU would spend over 90% of its time just walking back and forth to the pantry, just waiting for data to show up from the slower RAM. Registers pretty much eliminate all that waiting. The second big speed trick is something called pipelining. So instead of waiting for one instruction to finish its entire fetch, decode, execute journey before starting the next one, the CPU cleverly turns the whole process into an assembly line.
And here's what that assembly line looks like. Check out this chart. In clock cycle 2, while instruction 1 is being decoded, instruction 2 is already being fetched. By the time we hit clock cycle 4, we've got 3 different instructions all in different stages of the process at the same time. Once this pipeline gets full, the CPU starts spitting out one fully completed instruction on every single clock cycle. It's just a massive boost to efficiency.
So let's zoom back out. That simple, elegant cycle, fetch, decode, execute, that is the fundamental building block for absolutely everything your computer does. It's just this tiny, unbelievably fast dance of data moving between a handful of specialized little parts.
And that leaves us with a final thought to chew on. If this simple, repeatable cycle is the single atom of computing, then what does it mean that the device in your hand or on your desk is performing billions of these little thoughts every single second? The amazing complexity we see every day is really just pure simplicity, repeated at a scale that's almost beyond human comprehension.